Alright, this is Mr. Anderson for Math 130 Statistics for sections 4.3 and 4.4 of Chapter 4, dealing with the multiplication rules, conditional probability, and counting rules. Today we're going to look at the probability of AND. This is when we want one thing and another to happen. In the previous video we talked about the rules of OR, where we wanted one thing or another. Now, the first thing we're going to start off with is independent events. Now, an independent event, or two independent events, are those two events that do not affect each other. That's right, two events that do not affect each other. So an example of an independent event would be rolling dice. One die roll has no memory of the other die roll, or in the game of roulette, where you spin the marble and the marble spins around and it doesn't have any memory about what happened before. Dependent event would be like a game of cards. If you don't replace the cards after pulling the card out of the deck, it is technically a dependent event, where once you pull a card out, the odds of every other thing has changed in the deck because now there's one fewer card. Now, a lot of times people get the idea of independent events and they get that mixed up with mutually exclusive. Mutually exclusive events kind of have the same feel of independent events, but let's take an example that dice rolls are independent, but if you take the example that you want the probability of rolling doubles or a sum of 6, that's an idea inside of independent events where these two ideas are not mutually exclusive. So please do not think of mutually exclusive and independent as being synonymous, because here you have two independent things where you're rolling dice, but inside of that independent event where you can roll a die, you cannot say, oh, I want doubles or a sum of 6. These are not mutually exclusive, because in the Venn diagram of rolling doubles and getting the sum of 6, the intersection of the two is 3, 3. So getting a 3 and a 3 is not only a double, but it's also a sum of 6. So that's to hopefully clear that up a little bit, that I don't want you thinking that independent is the same thing as mutually exclusive. Alright, now we're going to move to when two events are independent, the probability of both of them occurring is shown by multiplying the probability of A times the probability of B. And it's shown like that. Now, what we're going to do is we're going to find the probability of A and B, given that A is getting tails on a coin and B is rolling 3 on one die. Well, getting tails on a coin, the probability of A is 1/2, and getting a 3 on one die, since there's only one 3 on that die, is going to be 1 out of 6. Multiplying fractions, not a problem. Top times top, bottom times bottom, 1/12. And you can turn that into a decimal, which is approximately 8.3% or 83 thousandths. Now, the probability of drawing a queen and then putting the card back in the deck and then drawing a diamond. So your chances are drawing a queen would be 4 out of 52, because there's 4 queens in the deck of 52. And drawing a diamond would be 13 out of 52. That's if you put the queen back in the deck before drawing the diamond. Now, multiplying fractions again is going to give you 52 over 2,704, which can be simplified to 1 over 52, which can then be the decimal written as 19 thousandths, or approximately 2%. Now, this is an interesting question here. If 55% of a high school classes are female, and what is the chance that 5 random searches will be all men? Can it be possible? It can be possible to pick the same person more than once. That way, if they pick somebody, it won't change the percent from 55% or otherwise. Now, I mentioned that 55% of a high school is female. So the probability of choosing a man would be 45%. So that's the odds of picking one person, one man. Now, if you wanted to see the probability, since these are all independent events, even though on a separate day or a separate time you could pick the same person again, it would be 45% times 5. Now, the faster way to do this on the calculator would be 45% to the 5th power, or caret 5. And if we multiply all those together, we get a decimal of 18 thousandths, or roughly 2%. Is this likely? No, not really. In fact, if your school is more women than men, and you're supposedly randomly choosing people to search, and they're all men, it's not a real random search, because the odds of that happening randomly is 2%. Now, here's a good question. What are the chances that they will pick up at least one female? Now, the answer to this is 98%. Because when we say at least, we have to think logically. Logically speaking, picking all men would be 0 women. And the opposite of picking all men would be picking at least one female. So when you see this at least qualification, understand that they're really looking for the complement of the event that you probably just found. So to find the complement, you would take your event and subtract it from 1. And that would give you your complement. So that's what I did. It was 2% to pick all females, or excuse me, pick all males. So to pick at least one female would mean that it wasn't the 2%, it was the 98%. Okay, on the second page. Now we're going to talk about dependent event notation. Now, a lot of times dependent events happen because the event A changes event B, like pulling a card out of a deck and not replacing it. So the notation for this is going to be the probability of A is going to get then multiplied by the probability of B given that A has happened. That line in the middle does not mean division. It just means that B occurs given that A has already occurred. So what we're going to do is we're going to find some probabilities, and we're drawing some cards out of a deck without replacement. I'll do the first one, and you should try to pause these YouTube videos if you want to see if you can get the answer before me. Alright, so the first one is getting 2 jacks in a row. There are 4 jacks in the deck of 52 cards. That means when you pull a jack out, you will then have 3 jacks left in a deck of 51 cards. Now, if you multiply fractions, this is going to be top times top, bottom times bottom. And you can simplify the fraction and get a decimal of under 1%. So it's a 0.5%, 5 out of 1,000. Not very likely to get 2 jacks in a row if you're pulling them out of a deck of 52 cards. Getting a 7, 8, and 9 in order. Again, please try to pause these and then check to see, try them out and then see if you're right. There are 4 7s in a deck of 52 cards. Then there are 4 cards, 4 8s in a deck of 51 cards. Remember, we pulled the 7. And then there are 4 9s in a deck of 50 cards. Remember, we've already pulled 2 cards out of the deck. And if you do your multiplication, and I'll skip right to the division phase, this gives you a much worse percentage. And in terms of rounding, where I usually say we round to the 3rd decimal, this breaks that rule a little bit, and we will round to the first non-zero decimal. Kind of a fun thing about multiplying fractions is that you can, on a graphing calculator, just type the fraction in with using the parentheses, like you see it. The parentheses already mean that they are going to be multiplied by each other. So I'm going to just do this problem out like so. And you'll see that this is a scientific notation problem. This decimal has to be moved 4 spaces to the left. 1 is going to make it in front of the point, in front of the 4, and then 3 more spaces will give you 0.00048, and we round that up to 5. So if you were using a graphing calculator or other calculator and got this exponential notation, this is why this has happened. All right. Getting 3 hearts in a row. This is going to be a little easier here because now you have more choices. There are 13 hearts out of 52, 12 hearts out of 51, and finally 11 hearts out of 50. Multiplying top times top times top and bottom times bottom times bottom, and then doing your division, this is going to give you about 1%, 1.3% to be exact. Now we're going to get a heart, spade, and club in that order. So 1352 is the heart, the spade is 1351 because there's 13 of the spades, and a club is 1350. Multiply top times top times top, bottom times bottom times bottom. You're going to get roughly about 2% there, or 1.7%. Now, what we're going to do next, and I want to kind of put a little divider line there since things got a little bit carried away there with number 6 not having a lot of room there to write. We're going to determine some conditional probability. Now there's a nice proof in the book. You should look that proof up. It's a very simple proof. It's easier than most geometrical proofs actually. But it explains that you can find the probability of when B occurs given that A has already occurred. You can do that by finding the probability of A and B divided by the probability of A. And this will find your conditional probability. Which means that you should have a smaller number in the numerator and a larger number in the denominator. This can get a little tricky. And one of the easiest ways to check your work is to make sure that your numerator is smaller than your denominator. That won't guarantee you'll have the right answer, but you should do a little self-check. You should have the numerator being smaller. So let's look at this definition and this little chart filled with pathologists, pediatricians, and psychiatrists. So I want to find out this problem here, which asks, what's the probability that they would be male given that we've chosen the field of pediatrics? So, following this procedure here, the numerator is the probability of A and B. So we want the probability of a pediatrician who is male, which is going to be 33,020, divided by the probability of A, the total number of pediatricians, which in this case would be the 33,020 male pediatricians plus the 33,351 female pediatricians. And if you add these up, numerator divided by the total number in the denominator, it'll give you roughly 50%, or 49.8%. Alright, now let's look at this. We're going to put our B and A here, because that fits our pattern up above. We want to find out how many pathologists there are, given the fact that we've only chosen the females. Well, let's go look at our formula here, the probability of A and B. So we're going to look at pathologists, or females who are pathologists, and that is going to be 5,604 over, now we're going to look at the probability of A, well, just picking all the females here, so 5,604 plus 33,351 plus 12,292. So we're adding up all the female list in that bottom. Divide the two, we get about 11%, or 10.9%. Now again, we'll follow this pattern right down here. Now if 72% this is actually taken from the book, if 72% play golf and are college graduates, so this is our A and B right here, this is our two conditions, that's outside of this country club, and 80% of the people in the country club play golf. Find the probability that a member is a college graduate given that the member plays golf. So, our probability of A and B is going to be the 72%. Because that's the probability that there is someone who plays golf and is a college graduate. Having already said that we're choosing only the people who play golf. Dividing these two will give you 90%. That is the odds that somebody, having chosen only the people who've played golf, this is the percentage of those who have already played, who are playing golf, who have the college graduate degree. Alright, now this is a multi-step problem, and I made this problem I made the numbers up out of my own, I just made these numbers up, so don't feel like they came from a study. But these numbers here kind of are similar to one of the homework problems you have that talks about high, medium, and low risk drivers. But in this case, what we have is high, medium, and low risk people for heart attacks. So let's suppose that 50% have a low heart attack risk, 35% have a medium heart attack risk, and 15% are in the high risk category. Now looking ahead, what we're going to do is find the conditional probability of each group who would have a heart attack. Now, let's say within that year we looked at those three groups, high, medium, and low risk. And then we took a look, and the low risk, only 5% had a heart attack. In the medium risk, 15% had a heart attack. And in the high risk, 10% had a heart attack. So what we're going to do is take a look at these three numbers. So we're going to start off with the low. Well, we're going to look at the probability that someone was in the low group and had a heart attack, and that was 5%. So there's our A and B. Out of the group that was the low risk, that's our A, and that's going to be 50%. That means we do the division there, 10% in that group. That's our conditional probability. Now we're going to go to our medium. Our medium risk group, well, there was in the numerator there, 15% were in that group and had a heart attack. There's our A and B. And then here's our A. That group had a 35% of the population had that chance of being in the medium risk group. So we do that, and that ends up being about 43% is our conditional probability for that. And then the high. The high risk group. The high risk group, well, there was, in that group, had 10% had a heart attack that year. 10% in that group, so there's our A and B. And then our A was the 15% of the population who are in the high risk category. And you'll see that that is a much higher number because the field is so much smaller. 67% basically. Or 66.7% exactly. Find the chance that a random person will have a heart attack, which is the final question of the one that's in your book. Now to figure this out, since these are three separate independent groups, we'll figure out this is going to be 0.1 times 0.429 times 0.67, and that gives us about a 3% chance, or 2.9%, that a random person will have a heart attack from these separate results. So when you do problem 21 in the book, that talks about the car collision chances. This is the process you'll set up to solve that problem. All right, now we're moving on to our final part, section 3.4, counting rules. Okay, here's the fundamental counting rule. Now, if you have possibilities, and those possibilities have k number of outcomes, like let's say flipping a coin has 6 outcomes, and you want to flip a coin 6 times, what you'll do is you'll multiply the 6 times itself 6 times, and you'll see that there will be that many possibilities. So the number of possibilities is k times k, that many number of times. Now, the best way to see this is to actually go to your book and look at some of the tree diagrams. To draw some of these would take a long time, but to give you the gist of what they're looking at, if you roll a die 6 times, so rolling a die is usually 6 outcomes. If you're going to roll it 6 times, you're going to have 6 to the 6th power. So you're going to have basically 6 sixes, and that's a lot of different outcomes. Quick reminder, to do exponents on your calculator, just use the caret key, which is above the division. So 6 to the 6th power would be 46,656 ways to roll 6 dice. And that would be 1, 1, 1, 1, 1, 1. And then 1, 1, 1, 1, 1, 2. And then 1, 1, 1, 1, 1, 3. And you've got 46,000 other ways to do this. Yikes. So that's rolling a die 6 times. How about flipping a coin 3 times? So if you want to flip a coin 3 times, it would be 2 times 2 times 2, or 8 ways to flip a coin. Or flip 8 different outcomes for flipping a coin 3 times. And then you can do some different combos of that. One of the neat problems in the book talks about paints. So for example, you can have like 5 colors of paints, and then there's 2 different styles. That would make 10 different styles. And then there's different types. So you have 3, so 10 times 3 is 30. So look for that in the book. But now we get into something kind of cool called factorial. And factorial looks like I'm shouting, N! But factorial is kind of a cool way to count it. Because when you do factorial notation, it's like multiplying, but instead of multiplying by the same number each time, you start off with the number n, and then you multiply that by n minus 1. And then you multiply that by n minus 2, and then multiply that by n minus 3, and you just keep going. You keep going, you keep going. n minus 1, n minus 2, n minus 3, on and on until you get down to 1. And that right there gives you some cool results. So when you look at 7 factorial, that's 7 times 6 times 5 times 4 times 3 times 2 times 1. And multiplying all those together, 7 factorial would mean that you'd have 5,040 different ways to take 7 items and do some fun stuff with that, and we'll explain that in just a second. But let's just kind of practice computing these. For factorial, you can pause the video and try it yourself. 4 times 3 times 2 times 1, that's going to be 24. 1 factorial is just 1, because it's just 1 until you get to 1. Now, by definition, factorial needs something for 0. Because you're wondering, like, well, is the answer 0? Well, by definition, 0 factorial is 1. Maybe a way to explain it is like, well, if you got 0 items, there's only one way you can have nothing. There you go. But that's by definition, 0 factorial is 1. Also, on the calculator, you can find factorial by clicking the math button, which is underneath the alpha key, scrolling left to get to the probability menu, and choosing option 4. Note that that puts the exclamation point at the end of the number you wanted. So let's say I wanted to put a 7 there. So 7 factorial should be 5,040. So that's factorial for you. But when is factorial useful for us? Factorial is useful when you want to take all items in a specific order. All items in a specific order. So, for example, you want to pick 7 items in a specific order. Well, how many different orders are there? 5,040. You want to pick 4 items in a specific order? There's 24 ways to do that. And obviously, logically, you want to pick 1 item in a specific order. Well, there's only one way to do that. Now, sometimes we don't want all the items, so we're going to define something called a permutation. This is a permutation is taking some items, not all of them. Take some of the items in a specific order. And if I might complain a little bit, this is technically a locker permutation, not a locker combination. Because when you do a locker permutation, you want the numbers in order. Look it up in the dictionary. Combination is not read with a specific order. Most of us think of combinations being in a specific order, but that really belongs to permutation. Look it up, Webster.com. Now, the permutation notation looks like this. It has a big letter P, and on the left side is an N and an R. The N is the number of items, so I'm going to move that off to the side here. N is the quantity, number of items. And R is how many you want. So this is the number of picks, or the number that you choose. Now, how you compute that, because you're not going to want all, like let's say up here, you're not going to want all 7 items. You're going to first of all take the numerator, which is n factorial, and divide that by n minus r factorial. Now, to show you that to you by hand, let's take a look at this one here. This is going to be having 5 objects and choosing 3 in a specific order. Okay, so the numerator is 5 factorial, and the denominator is 5 minus 3 factorial, or 2 factorial. Alright, now what's a fun way to compute this, and I'll show you this, you can actually type this out. You can go 5 times 4 times 3 times 2 times 1, and the denominator is 2 times 1. You can do some simplification. 1 divided by 1 is 1, 2 divided by 2 is 2, so your answer is 5 times 4 times 3, which is 60. There are 60 ways to pick 3 items out of 5 in a specific order. Now take a look at this one. This is having 7 items and choosing 4. The denominator is 7 minus how many we're choosing, so 7 minus 4. This gives me 3 factorial. Now let me show you a way to do this problem just a little bit different than what I wrote here. I'm going to write 7 times 6 times 5 times 4 times 3 factorial. Instead of writing 3 times 2 times 1, I just kept that as 3 factorial. Now you'll notice my denominator also has 3 factorial in it. You can simplify those and they divide to make 1. All of these answers will be whole number answers because you're just counting the number of ways to arrange them in order. So this is going to be 7 times 6 times 5 times 4, and we have 840 ways to do that. 840 ways to pick 4 items out of 7 in a specific order. Now, on your calculator, there is a way to compute permutation without going through all the busy work with the work here. You go to a clear screen and type in the number of items you have. In this case, having 6 items, choosing 2 for a permutation. We're going to type in 6 first. Hit the math key, move to the left, and then choose the second option on your screen. And notice that fits the pattern, but we're only choosing 2 items there. So that fits what the problem is asking. Choosing 2 from 6 in a permutation. Bloop! Your answer is 30. Pretty nice. Now that's a permutation. That's where we're picking items in order. For our last page today, and our last examples, we're going to talk about combinations. And combinations are going to deal with choosing items without order. So taking items is in a set without order. Taking this item in a set without order. Now, the combination notation is like before, where n is the number of items in our set, and r is going to be how many choices we want, and the equations are almost the same. You'll notice that this equation is exactly the same as the permutation notation. But there's one more thing to divide by, and that's by r factorial. So, let's take a look at this list here. This is, and I'll kind of keep this in the same screen here so you can evaluate it. We've got 5 items and we're choosing 3 in order. So my numerator is 5 factorial. My denominator is 5 minus 3 factorial, see n minus r, so that makes 2 factorial, multiplied by 3 factorial. Now let me write all these out and show you how things simplify very easily. The numerator is 5 times 4 times 3 times 2 times 1. The denominator is 2 times 1, and then 3 times 2 times 1. Look, we can do some simplification. 1 divided by 1, 2 divided by 2, 3 divided by 3, they're all 1s. And 4 divided by 2 is going to leave me a 2 up here. So 5 times 2 times 1 times 1 times 1 over 1 times 1 times 1 times 1 times 1 gives me 10 over 1, which is just 10. There are 10 ways to pick from 5 items, 3 in any order. This reminds me of a Price is Right game, where you have 5 items and 2 of them are the ones you shouldn't pick. So you have 10 possibilities, 10 ways to win that game. If you have to pick the 3 items or there are 10 ways to pick the 3 items. Remember, order doesn't matter out of those 5. Alright, now we're going to do this one a little differently. I mean, it's still the same process. The numerator is the 7 items you have. 7 minus 4 is 3 factorial, and then the 4 factorial for the last part of this equation. Now, it's a misconception to say that 3 factorial plus 4 factorial is 7, so the whole thing's 1. Couldn't be farther from the truth. 7 factorial is like saying 7 times 6 times 5 times 4 factorial. Notice I didn't write out the rest, 4, 3, 2, 1. Because in our denominator, we've got 3 factorial times 4 factorial. Look, we can simplify those to 1. So now we have 7 times 6 times 5 over 3 times 2 times 1. And we can do some more simplification here. 3 times 2 is 6, which simplifies with that 6. So we get an answer of 35. Again, I strongly encourage you to pause this worksheet or this YouTube video and try some of these by yourself before you have seen me do it all. Okay, try this one. You're going to be kind of surprised with the answer here. You've got 10 items and you're going to choose 9 of them in order. How many ways can you do this? Okay, hopefully you've tried this on your own. This is 10 factorial. 10 minus 9 is 1 factorial divided by 9 factorial. And again, you can decide to do this all on the calculator if you want to. You can use parentheses and do 10 factorial, like so, divided by, now 1 factorial is 1, so I'm not going to bother putting in 1 factorial, but then I'm going to multiply by the 9 factorial here. And again, I'm chuckling a little bit inside because I already know the answer, and it makes sense if you had wrote the problem out longhand. 10 factorial divided by 9 factorial is just 10. And it's 10 because, think about that logically. If you're choosing 9 items in any order, you're basically going to have only 10 different options. Because if your 9 items can be in any order, you're really going to have 1 can left out. That's 1 item. Then 2 can left out. Then the 3rd can left out. So basically you only have 10 options because you're really only looking at the cans that were left out. Alright, and my final example here is going to be tribute to my home state, Michigan, because they have something called the Classic Lotto. And the Classic Lotto has 47 numbered balls to choose from, and you got to choose 6 in any order whatsoever. The jackpot starts at $1 million, and it goes up from there. And the highest I've seen it crawl is, I've seen it up around 10 million, but, usually it takes a long time to get there. So here's how you do this. 47 factorial divided by 4 factorial, because this is, or 41, factorial, because 47 minus 6 is 41, and then 6 factorial for that last part of the formula from up here. Okay, 47 factorial divided by 41 factorial times 6 factorial. You might think that this would be a really, 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 really long problem. But really, you can make this easy on yourself by going 47 times 46 times 45 times 44 times 43 times 42 times 41, but then crossing out the 41s, and then taking that sum at the top, or that multiplication at the top, 47, 46, 45, and then divide that by 6 factorial. When you get to the final answer, however you do it, you get 10,737,573, which is ingenious, because in a lottery that has only a $1 million or $2 million jackpot, you'd actually be spending more money to buy every conceivable ticket before you actually win. And the fun thing about that is that I don't think those printers at the gas station can print off 10 million tickets in the span of a week, but it would sure be interesting to see if that would be possible, or at multiple gas stations or something like that. All right, well, that is the end of Chapter 4 here, and our next class session is going to be talking, we're going to be looking at a review test to go over all 4 tests, or all 4 chapters for our first major test. All right, thanks for watching.